This is part 1 of 7.2 volume of cross-sectional areas, and then I'll do a second part. So we'll do the first 2 examples here and then the next 2 examples on a different recording. What you'll want to note here is that the volume is equal to, let's choose a different color, volume is equal to the integral from A to B of the area of my cross-section multiplied by dx. So this is going to pick up area of the cross-sectional piece. And then if I multiply that by the thickness dx, we will pick up volume, and then we'll accumulate volume here. So what does this look like? Well, these figures, what we're going to do is, notice here's the thickness dx, or delta x, and I'm going to set a square in on this one. So there's this face here that's going to be covering the base, and you can kind of see the shape of this base. We're going to set a bunch of vertical squares in on this, and it will give us this overall 3D appearance as you see in the picture. In order to get volume of a shape, such as this, what we're going to do is calculate the area of one slab here, and then take it by its thickness dx, and that will give us volume. So this first one, what we're going to look at is the volume of a solid whose base is the region inside a circle. And here's our circle formula, x squared plus y squared equals 25. If cross sections taken perpendicular to the x-axis are the following. So I'm going to put in squares and set them perpendicular to my base. So here's the circular base. If I tilt it and tilt my axes, x and y, you can kind of get a better look at this. So look over here to the left, and here's this square cross section that's going to fit in. And if we fit a bunch of them, it's going to give you a 3D image that looks like this. So what do I need to do? Well, according to the formula, what I need is an integral going from A to B of the area of this square. So what I need to come up with is what is the area in terms of x, and then I'll dx it, multiply it by the differential. Little a would be here. This is actually b. Little a sits in the back side, and since it's a circle, this correlates to my little a, and this here is my b for the circular base that we're going to set our squares perpendicular to. So we can see here that little a is equal to -5 and little b is equal to 5. So when I integrate, I'm going to be integrating from -5 to 5 on this one. Now, the whole work part of this is really coming up with the area of the perpendicular cross section. And we're going to use squares in this example. So I'm going to erase this for now. My square is going to sit as a chord across the circle. So what I need to do is figure out what this base's length is across there, or the chord length. And that would correlate to this distance across here. So this is the length across the circle, which gives us the dimension of our square. I'm going to solve this for y. I'm going to have y squared equals 25 minus x squared. Square root this, and y is equal to plus or minus the square root of 25 minus x squared. Why the plus and minus? Well, the plus and minus are necessary because the red part of my circle, the upper portion of the circle, would relate with y equals the positive 25 minus x squared. Above the x-axis, I've got positive y, so I want the positive square root there. Below the x-axis, we're talking about the negative y values. So in this case, y is equal to negative square root 25 minus x squared. So now I can calculate the full distance across my base, and it would be the top function minus the bottom function. So I'm going to go in here and work on the area of a square. And that area of the square, in terms of x's, would be the base length times the base length, right? A square has equal dimensions for width and height. And according to our picture then, I want to capture that chord length, and the top function is square root 25 minus x squared. And the bottom, oops, I need to put a minus in here. The bottom piece is negative square root 25 minus x squared. And that will represent the total distance across our circle. Top function minus bottom function. And then I'd multiply it by itself. We'll square this. So let's just simplify inside first. I'd have 2 square root 25 minus x squared when we add them together. And then we want to square that quantity. So squaring that would give us 4. Square root is gone. So I'd have 4 times 25 minus x squared. And this is representative of the area of the square cross-sectional piece. As x changes, so does the area of the square. So when I have squares in front, they're quite small. As the chord length starts lengthening, my squares begin to get taller and taller as that base gets wider and wider. So now it's quite easy to put this together. Volume turns out to be the integral. We said we were going to go from negative 5 to 5, working our way across the circular base. And I'd have 4 times 25 minus x squared dx. Remember that this is really representing the area A of x. And I have put that into my calculator and came up with 666.667 units squared, or units cubed. That's one example using square cross-sectional pieces. The next one we go into is going to use equilateral triangles. And I just want to see where we're at on time. We've done 7 minutes. Okay. So we're going to do equilateral triangles against this base again. I'm going to clear that, and I want to bring this picture down with me. So once again, we've got this circular base, and we know that the top function was the square root of 25 minus x squared. The bottom function here is represented by negative square root 25 minus x squared. Total distance across, we did a calculation before, and we found out that that base length was 2 square root 25 minus x squared. Total distance across there. Well, that's going to be the same distance across then my circular base. This would be that base length again. So the base length is the 2 root 25 minus x squared. Since I'm working with an equilateral triangle this time, my geometric calculation has to be a little different. So I've got this height sitting in here because I know the area of a triangle is equal to 1/2 base times height. So I need to capture the height, and I need to capture this base. But I know the base. I just had it figured out from last time. Base is equal to, I'm going to move it down just a bit. My base is 2 times the square root of 25 minus x squared. Now, a little bit of going back for you. Think about your 30, 60, 90 right triangles that you learned in geometry. Also, they form part of the foundation for a unit circle. So, in a 30, 60, 90, across from the smallest angle is the shortest side. So this is my short leg, as I like to refer to it as. The longer leg of the right triangle, across from the 60-degree angle, is larger by a factor of the square root of 3, and then the hypotenuse is 2x, twice the short leg. So I can use that knowledge to help me build the values on this. So this whole base was 2 times square root. So that means the halfway point, each of these segments would be 25 minus x squared, and this side would have been square root of 25 minus x squared. Up here, my height, using this knowledge, to get from short leg to long leg, I multiply by the square root of 3. So I'm going to have root 3 times the square root of 25 minus x squared. And from that, I can now figure out the area of the triangle. So the area of the triangle is 1/2 base times height, or 1/2 the base to root 25 minus x squared, because I want the full base, right? And then multiplied by the height, which we calculated to be root 3 times the square root of 25 minus x squared. A few things are going to simplify here. We got the 2's canceling, and then I have root 25 times the root 25 minus x squared times the root again. So I will end up with that root 3 times 25 minus x squared. I just got the main key ingredient to get this done. Now into the volume calculation, which involves your integral. So the volume is the integral from little a to b, and my little a in this case is at -5 on the back side up to 5 on the front side. Remember, what we're doing is we're traversing across our x-axis starting on the back side of that circular base, cut across to the front side. So I'm going from -5 to 5, or seeing it here, -5 to 5, just like we did on the square. A of x, so I've got root 3, which I could pull out in front of my integral, 25 minus x squared dx. Area times depth, or thickness, gives us volume, and we are going to accumulate the volume. So final answer, 288.675 cubic units. All right, on to part B.